things at once. Oh, Bobs and Y can't make it. Um, do 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 do. Boop boop. We should have a little jingle for this series, so that at the beginning when I'm trying to figure it out, can have a little boop 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 doop 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 boop boop. Okay. Looks like we're online. So hi. This is part 2 of JSFX Scripting with my good friend Leandro above me. And last time, last time we did a little bit of an intro, and we'll do a little review in a second, but I'll let Leandro say hi first.
Hello, everyone. Thanks for having me here. It's always a pleasure to stream with you.
Favorite part of my day. Even my week. And now, actually, we are going to have another stream tomorrow on your channel.
That is true. So, for people who are interested not necessarily in the coding aspects, but in the recording aspects of ReaPIR and audio production and content creation, then we are going to talk about that. I think that we'll start by talking about gear. It's always a nice icebreaker. So, we'll talk about the different microphones and instruments and monitors, that sort of thing. And every Wednesday on my channel, we will talk about different topics in that space. So we'll talk about how to record instruments, how to do post production, how to edit, to do EQ, like the EQ that we are developing. We can try to use it in an actual song. That's that kind of thing. Yep.
Yeah, should be fun. Tomorrow's the first one, so join us on Leandro's channel this time. Oh, hello, Gen MCE. That's how my instinct tells me to pronounce that. Thanks for joining us. Bops NY. That's okay. We'll view it later because I actually have a little demonstration for you in a second. So how about we start by kind of reviewing what we've done so far, um,
Yeah.
which is, we did a lot and we talked about um, a lot of stuff, but our code itself is pretty simple so far. Um,
Yeah.
okay, so I'm gonna try and do a review, and then you tell me how, if that was okay. Um,
Sure.
so JSFX, when it comes to JSFX, we are working with EEL2, so it's no longer Lua. EEL2 is developed by Kakos and by Justin Frankel. So it's very well integrated into ReaPIR, but if you want to use it in another DAW, that's harder. On the right side, when you so if you let me even do the procedure real quick. You can right click up here on the right pane of your FX browser, and you can create a new JSFX. You can call it something, and once you do that, you can drag that to any track, which is right here, and you can hit this edit button, and it will bring you to this window. And this window should be familiar for JSFX folks, but it's a little bit different. So when you see when you open like a very stock JSFX that you just created, you see a few blocks here on the bottom, each starting with an @ sign. So this is the initiation block, something that happens when you begin your when you kind of launch your plugin. So we got rid of this because we're doing an EQ. This is the slider block. So this is what happens when a slider moves. And we got rid of that. And these are the kind of connectors that you would see on top of any plugin right here, the plugin pin connector. So I'm assuming we can add extra things here and do all sorts of extra stuff with that, but we can also get rid of that. Currently, this effect has one slider, but you can add more sliders. Slider 1, 2, you give them a variable here, like this is the variable they control, so it can be something like gain 2 underline dB. And then in front of it, you have the default value, and then in breaky brackets, you have the first value would be your minimum of the slider range, maximum of the slider range, and step increments of the slider range. This is the name that's displayed to the user, and if you put a minus here, it'll be like a hidden slider, which can be used for like more advanced features. And then we got rid of this block as well. So we are just working on the sample block. So now I'll just close this. Let's not save it. Let's remove this. So now we arrive at our script, which on the sample block has a very simple kind of thing so far. So we got this average amount that we are taking, and we have this previous sample. So the previous sample is equal to sample 0. That's what's going to your channel 1, output channel 1. And since we're doing a mono, we're doing, well, output channel 1 and output channel 2, which is SPL0 and SPL1 being the same thing, and they're equal to the average. And the average is previous sample, which I think I messed with this a little bit. I think it was times 2 plus SPL0. So we're taking an average of every previous sample with the current sample every time this plugin is running in sample speed. It's taking the previous sample, it's taking the current sample value, and it's taking an average of them, which will give us a high pass filter. So far, tell me how wrong I was, Leandro.
You are absolutely perfect. Yeah. One thing that you said that JSFX work in ReaFIR only, and that is only half true. There is something called replugs, which is a bunch of ReaFIR plugins you can install and use. Yes, wherever you can load VSTs, you can load RIA plugs. And there is a replug in the kit that allows you to run JSFX in other DAWs. You can run your JSFX in OBS, anywhere you can load a VST.
Oh, cool.
But there is a limitation. There are some limitations. The first limitation is a pretty big one. It only works on Windows. So I know that you're running macOS right now. You would not be able to run your JSFX in Logic, for instance. That's not possible. And the second limitation is that I think that the last release of replugs is like, so that's the guy, ReaJS. It allows you to load JSFX in other DAWs on Windows only. Doesn't work in macOS, doesn't work in Linux. The second limitation is that the replugs have been updated for the last time in like 2016, 2018, something like that. Has been a long while. And the version of JSFX that you can run is older, and there are some things you cannot do with older versions. So there are some limitations, but if your effect is relatively straightforward and basic, then you may be able to run it on different DAWs, which is kind of cool.
Oh, cool. I knew about RIA plugs. I didn't know about ReaJS because I guess we don't have it because we don't need it. But cool. So yeah, but you know, if you're a Mac user, for all intents and purposes, JSFX it will be a little trickier to set up in other DAWs. You're tying yourself to ReaFIR a little bit, and obviously we got tutorials to show you how to plug other DAWs into ReaFIR, like get audio from other DAWs and process them in ReaFIR, or send MIDI out from ReaFIR and process them in other DAWs and stuff like that. So check those out if this sort of thing is your sort of thing. Bo is asking, I thought the code reads from top to bottom, so how come previous sample comes after the average variable? And I guess the reason is like this is running, 48,000 times a second. So maybe for the first sample of the plugin, there's like no value there, but then it runs this in 148 thousandths of a second, and then that value is constantly populated and updated, right?
Exactly, yeah. That's what happens. This sample block of code runs for every sample, and the variables from the previous sample just hang around for the next time. So we define previous sample in one pass of this. Effectively, it's a loop. It's running in a loop. So we are defining the previous sample in a loop, and then we are using the previous sample the next time we go around. To begin with, the previous sample is 0 because every variable in JSFX starts with 0. But starting on the second sample, it is actually doing the right thing and taking the average of the two previous samples.
Um, and actually, last week it was really hot here. This week is not much better, but I was completely um, out of it last week. And Bob's NY asked that he didn't understand this average situation, and then I, like a dumbass, explained to him the concept of averages, which he was clearly familiar with, because who isn't, beyond fourth grade. So I actually have a little demonstration of why that thing is, that I can quickly go over. So I got here like I got here 8 sine waves, and the first one is 100, second one's 200, 300, 400, 500, 600, 700, 800. So if we look at the parent folder, we see right now the sound wave of the first one. If I start unmuting others, oh, this is annoying. Yeah, it doesn't show actually the wave as it is. Let me just quickly record this and show. So get rid of the metronome. So right now we're just recording the sound wave. Second overtone added. Third overtone added. Fourth overtone added. Fifth. Sixth. Seventh. Eighth. And then I'm just gonna get rid of 8, 7, 6, and 5, and even 4. And the loudness of these are different too. So if we look at the waveform of the sine wave, when it's a sine wave, it's just going up, it's going down. So the values would be like 0, minus 0.5, 0, plus 0.5, and it's going like this. Then we add the next overtone. This may take a while. There we go. So we add the second overtone, and now these two sine waves are being added to each other. So the bigger kind of peaks are when their peaks match up, and this little dip within their dip, that little like protrusion, that's when the, double timed sound wave is poking through. And we keep adding overtones, one more, one more, one more, one more, one more, one more. And by the time we add like 8 or 9 overtones, we are getting to this complex shape. But you can kind of see the outline of the first sine wave kind of underneath all of this jagged stuff that we see. So in essence, once we take an average of this line starts to get a little more straight, starts to resemble this sine wave that we see below it a little more. Therefore, by taking averages, we are making the wave a little smoother. All those very kind of small different changes in frequency, like those small quick updates of values, get smoother. Therefore, low pass. Was that a good explanation, Leandro? Anything missing or anything you want to add to that?
Yeah, I really like how you showed the waves, and the waves actually look like the graph that we saw last time. That I think it was a stock market thing. It was varying very fast, so the rate of change was high, And then there was this averaging algorithm that was running on top of it, and it would smooth out the fast variations, but it would keep the general trend. And that's what a low-pass filter does. And we are doing that just by looking at a pair of samples and taking the average. So if they are changing fast, a pair of samples will be far apart, but we are taking the average, so we're smoothing that out. And if there is some change that occurs over a long period, then we are just averaging every pair, so we keep the trend.
Exactly. And it was, what was it, the Hull moving average? And I guess just to show
Yes.
the reverse of that, what happens when we do the old high pass. So this time I'm going to record and I'm going to kind of cut these back. So with the other one, we were taking two samples and we were deducting them from each other. Deducting them? I'm bad at mathematics terms, by the way, because I learned mathematics in Farsi and now it's English. But so we kind of took the differences out, which is, you know, the big differences are these are dictated by the lower waves, and what we're left with is the higher sound waves. Because if the difference between two samples is a lot, then this value would be higher. If it's not a lot, that value will be lower. So we start with this, and as we kind of start getting rid of the lower overtones with mathematics, we are getting to like more changes. And of course my overtones are quieter, so we're losing loudness, but that's not a product of the math. I guess in essence also lower frequencies carry so much energy that when you do a high pass, you're going to lose some volume like that as well. So that was for you, Bob's NY. Hopefully that makes a little bit sense. And splap. Oops. So yeah, so what's next for us, Leandro?
Well, there is one thing that we forgot to do,
Oh.
which is so important when you're doing audio effects, and that is to actually listen to the result. We looked at the graph and we know that we are doing a high pass or a low pass. We actually did the two in the previous stream. So we know how to do them. We just take the average of the samples or we subtract the samples. When you take the average, you are doing a low pass. When you subtract, you are doing a high pass. But what we never did was to actually listen for the
That's
change.
true.
So how about we are now running white noise through our effect, and it would be lovely to actually hear the effect and see if we can tell that we are doing a low pass and a high pass.
Sure. I am going to bypass this. And yeah, tone generator is already bypassed. I'm going to slowly bring this up. Lovely white noise. I think that's pretty loud. So yeah.
I am not hearing anything. Are you giving me the same audio feed that you're giving to the stream?
Oh, I may not be giving the same one to you as the audio feed. No, I am. Something is missing here. Sorry. Let me turn this down. Oh, see, I gotta check everything before my streams. So I apologize. Now you should be hearing this situation. You hear that?
Yeah, I hear it very well.
So that's some white noise. And right now we are taking an average of previous sample and the current sample, dividing it by 2. So turning this on. Off. On. Off. On. And what I'm actually hearing also is like it's got a nice cue. It's got a little bit of a resonance, so I can feel the high end going away, but just at the corner of where it's like starting to go away, there's a slight boost. Did you hear that as well, Leandro?
My ears are not that well trained, so no. That's why we are having that session tomorrow and every Wednesday.
Cool.
So maybe I can develop these skills.
Yeah, and it's hard to tell with white noise if it was another type of sound. Maybe let's test it on another type of sound too. What do you say?
Yeah, sure.
Our high pass or our low pass also, I guess, is right now we don't have too much control in terms of like the Q or the cutoff frequency and stuff like that. So this would be a very it could just be really subtle to begin with. But let's listen to this sound. I'm gonna turn it down because I have no idea what this sounds like. Oh, okay, this is what it is. So it's just a little patty situation. And I'm going to add our little random EQ to it. Sorry, tons of stuff going on. Random EQ. Put her there. Oh, I thought I looped this. Oh, and I guess our EQ right now is mono. So let me actually mono this as well, just so we get like an objective A/B. So without it's very subtle right now.
I don't hear anything.
Yeah. It's
maybe maybe the high pass will be more noticeable.
oh, okay, yeah, let's try that. So I guess that brings us to a question that, like, once I save this, all instances of this EQ will receive the update that this code changed, right?
I don't remember, but I think that if you have multiple instances running and you save, just the one that you saved will pick up the changes, and you have to like interact with the other ones for them to be picked up. So maybe you have to bypass or you have to edit them and save or something. I don't remember.
Okay. Well, like just kind of clicking on this one and looking at edit, it seems like it got the change, but we can do tests of this. So let's.
Yeah. So the file underneath your every JSFX is a text file on your file system. So it's literally just a .jsfx file on your disk, and the file is the same for all instances of the effect. But I think, if I remember correctly, that ReaFIR tries to be smart and fast and tries to cache some of these, so it loads the file from memory, and you have to interact with the effect to force it to go and fetch the file from disk again. But I may be wrong.
Well, I guess let's see if we can hear the low pass now. I also don't hear that too much. I mean, this sound, I guess, doesn't have too much low end to begin with. Let's see what else I got. Oh, I got a really low endy piano right here. Let's do that. Let me copy this, paste it here. I'll turn off this delay for a sec. And actually, I'll bypass this as well. So a nice low endy drum. Ooh, got hella quiet. Oh, because again, it's a stereo. This is so far a mono effect. Sorry about that. Okay, so before. It gets really quiet.
Yeah, it gets rid of the low end, all right.
Yeah. Yeah.
Okay. But I think I have to say this. I think that our effect sucks.
So far, nothing special.
I think that we need. Yeah, I think that we need some sliders to parameterize the cutoff frequency, and I think that we need to be able to tell how much we want to cut. And I think that's what we need to do today. I think we need to fix this because it kind of sucks.
Yeah, I can.
What do you think?
Yeah, I agree wholeheartedly.
So I was thinking about something that I forgot to explain last time, which I think is super interesting about, or at least I find interesting, about the way that the EQ works, the mechanism by which this EQ works. So we talked about this rate of change and how you can manipulate samples to manipulate the rate of change. So you can do like an average of the samples to get rid of the high frequency changes. But there is another way of thinking about this. I remember that last week you said that you learned max DSP, and the person who was teaching you said that, oh, how do you want to start? Pick an effect that you want to do. And people said, let's do an EQ. And the person said, no, an EQ is actually not the simplest. It's the hardest thing to do. And then you gave an example that is perfect. It's much easier to do something like a delay. Just get a hold of the sample where you remember it and you replay it a couple, I don't know, seconds later or something, right? Yeah, so let's think about what these 3 lines of code we have on the screen are doing. They are doing, I guess, let's do the previous sample plus SPL0. So it's the average, it's the low pass filter. I think that is the best way to explain what I'm trying to go for here. So what you're doing here is you are taking the average. By taking the average, it means you're taking a previous sample and adding to the current sample. And another way of thinking about this is that you are playing the previous sample along with SPL0. We saw this last time, how you can add 2 samples to effectively play them together. You're merging the samples together, right? So what we are doing is we are merging these samples. So effectively, what this is it is a delay, but we are not delaying by 200 milliseconds. We are not delaying by a quarter of a note. No, we are delaying by 1 sample. It's a 1 sample delay. So I find that your example last time is perfect because you said that an EQ is kind of hard, or the person who was teaching you said, an EQ is kind of hard to do. A delay is simpler, but an EQ is a sort of a delay.
Yeah.
That is crazy. But it gets crazier. Because do you follow Adam Neely
I love the guy
on YouTube? Yeah. Yeah, so Adam Neely has this awesome talk he gave that, I think, in Berlin at Ableton. Ableton. There was a conference. I think it's Loop, the name of the conference. And what Adam talked about is this idea that rhythm and frequency are the same. If you think about rhythm, you're thinking about... And if you think about frequency, you are talking about low versus high. And they are different experiences to us. One is something that happens over time, and you can tell each pulse as it's happening. You can tell the pulses apart. But the pitches, the low versus high, you cannot a certain number of seconds. You don't feel that wave. What you feel is just pitch. So they are different perceptions, but underneath the physics is the same. When you are clapping, you are making a wave. And when you are doing different pitches, you are also making waves at different frequencies, and they have different wavelengths, but we perceive them as different things, but they are the same. So if you have a delay, a typical delay of like 200 milliseconds, you clap, and then you hear the clap again 200 milliseconds later, and you perceive that as an echo. You are on a canyon, and you hear the slap back. But if you take claps, and you maybe record a clap, and you start to speed it up, it goes like... And then it gets so fast that you start to hear it as pitch. It goes like doom, 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 doom. I'm trying to reproduce with my voice the effect that you hear if you try to do that. So if you try to play some claps and speed it up, you start to hear this difference between rhythm, and there is this gray area in which it could be perceived as rhythm or as pitch, and then you clearly perceive it as a pitch changing. And what we are doing with this delay is the same. You can take a delay of 200 milliseconds, and then you hear a slap as you are on a canyon, and you can hear the echo. But then you start to hear the echoes getting closer together, and they get closer together, and they get closer together to a point that they become differences in pitch, and you hear that as the effects of an EQ. So the physics of the EQ that we have and the physics of a delay is exactly the same, because rhythm and pitch are the same thing. Isn't that fascinating?
Yeah, it's incredible. I love that talk by Adam Neely, and I'll put the link in the description once we're done streaming. It's also just really cool that, yeah, like I remember on like old drum machines and stuff. Sometimes, like I had an old Electri by Korg, and it didn't have too much like in way of EQ, but it had this delay effect that you can put on different modules. So if you really wanted to kind of slightly EQ something, you would bring the delay amount really low, and when you were going from like 0 millisecond to 30 millisecond, in that region you would get a change in tone more than perceiving anything as any kind of delay. Then once you go over that, we call it the Haas horizon, so the Haas threshold, where we start to hear two things as being separate. It's about 30 milliseconds. And also, I guess wavetable synthesis works this way, right? So you can take a snare sound and use that to make a synth sound. Or you can even try on ReaFIR, like put a snare sample once every second, and in essence that would be like a 1 hertz situation. Then glue the whole thing together, then you can stretch it back so it's 1 second, and you will hear 100 hertz tone. You will hear all the overtones that come out of the way that the snare sound is different from a sine wave. But yeah, you can take any sound as, because sine wave is like this sound that we repeat 100 times a second. So you can take any sound and repeat it 100 times a second, and it will create a pitch. And it would have a character and an overtone character that's coming from the wave form. So it's really cool. Like, and I think what you were saying the other day, like, really stuck with me too. Like, every bit of music that you've heard in your entire life, and every sound you've heard ever, like, it's just -1 to +1. And really, these values alone aren't enough to show us anything. Like, if I just see 1, that means nothing. It's really about how fast the value is changing that, like, we get musicality from. And if we slow that rate, then we're getting kind of more in the realm of rhythm. And we speed that up, we get into the realm of pitch. And I guess above pitch, something else.
Yeah, well, if you go really above pitch, you start to see light.
Right. That's insane. Yeah.
Well, not really, because one is a physical. Yeah, I think that's the name that they use, right? It is a physical wave. It is moving air, and the other one is electromagnetical. But the frequencies are still what you perceive. So in any case, I find that fascinating, and I thought, well, and I also find fascinating that you could actually use this musically in an instrument that didn't have any sort of EQ, and you did you find it out by yourself that you could use the delay as an EQ?
I think it's somewhat of a known trick in drum machines. Yeah, I don't think I was the first to discover it or anything. Yeah.
I knew that this was a thing. I didn't know that people actually used it on all the instruments. That's fascinating. So yeah, we have a 1 sample delay, and this 1 sample delay is our EQ. In this case, the one we have on the screen is a low pass EQ. But what if we had So we were doing this by the end of the last stream. We were playing around with the values. You can put more of the previous sample and less of the current sample. And you do that by just multiplying the previous sample by a number, or vice versa. And that will have an effect on how much we are doing the EQ. So now that you've multiplied by 2, I think that the EQ is probably not as intense. It's hard to tell. The effect is so little in the end, but it has a different effect. But what if we go 2 samples behind? What happens then? Do you have an idea?
So we will get averages from 3 samples instead of 2 samples. So I guess we are in essence bringing this level back, like the cutoff of our low pass will be brought back, right?
Yeah, I was thinking about something even simpler. You don't mix the previous sample, you just mix the previous to previous sample.
Oh, okay.
So on the end of the last stream, we played with the idea of mixing more or less of the previous sample into the output. Now I'm saying instead of playing with how much, let's play with time.
How many times?
Let's go 2 samples behind. And so let's try that out. Besides having the previous sample, let's also have a verb. Oh, by the way, since Bo asked for this and it seems to be counterintuitive, here's something that we can write in the code that will have absolutely no sonic effects. We'll not hear any difference, but the code may be clearer. So here's something we can do. We can do, before the sample block, we can do an init block. And there we can say previous samples equals 0. And this will have no effect because, as I said, a variable that doesn't exist, like the previous sample variable on the first line of, or on the line that is calculating the average, so the previous sample did not exist, so it was 0. So saying previous sample equals 0 is redundant. It doesn't change anything, but it may make things simpler to read. Because the person will see, oh, there is a variable called previous sample. It starts with the number 0. Okay, that is the default in JSFX. Every variable starts with 0, but now it's more explicit, and we are communicating the intent better, and may make things easier to read. What do you think?
Yeah, that's a great idea, like to make it more readable from the human point of view, because it's hard for us to process things 48,000 times a second, I guess, or verbalize it in any way or read it. I also was noticing as I was A-Bing the EQ, there's a little click because that drops suddenly. So I guess, could we use the init block to somehow introduce some kind of a, like, what do you call it? Like a fade in, like a pad in when the EQ kicks in so that we don't hear a click?
Yeah, so hearing clicks is a big issue because it's not just when you start the effect, when you bypass something and you stop bypassing it. It's also an issue if you're automating a slider. You don't want that change in parameter to result in any kind of clicks. And there are all sorts of games you have to play to make sure that you'll not hear clicks. In fact, the boilerplate code that we played with last time and that you showed this time as well, it is a very simple effect. It's just a slider for volume, but it is slightly more complicated than it should have been because it prevents clicks. So the way we could do this is we could have a variable that starts with, so there are multiple ways of doing this, okay? But one way of doing this is to have an init variable that starts with 0, like an attack variable. And then on the sample, we would look at the attack and we would multiply by the attack, for instance, the previous sample times attack, and then we would increase the attack up to 1 maybe. So it would have a ramp up instead of just being an instantaneous change. But because we are just beginning here, let's not worry about this too much.
Yeah, cool.
Yeah, but if you want to do more robust effects, then you have to think about that as well. Depending on the parameter, right? There are parameters that you would like to automate. There are parameters that it doesn't really make sense to automate. So in those cases, you don't have to worry too much about it, and you can let the click happen. Yeah, and this whole line of thinking, let's make this easier to read, let's have a previous sample equals 0, something that unfortunately you're not going to find too frequently in code that has to do with manipulating audio. People usually use short variable names. So instead of saying previous sample, they would just say like x0, and they will not have this initialization block. They would just know that the variables start with 0, so I'll just use them. And I learned a lot of what I know about audio effects by reading other people's code. And unfortunately, it can be a struggle sometimes, but at least we have that view on the right that helps, because we can at least tell what the variables stand for, what are their values. Yep. You need a semicolon at the end of the previous sample equals 0 line.
Syntax.
And now we will add a previous sample. I don't know if you want to call it that way, but it will be 2 samples ago.
Let's call it
So
that.
we can do in the init block.
2 samples ago.
Yeah, that's fine. And in the init block, I recommend that we also put the 2 samples ago equals 0, just to say this is a variable that I'm about to use.
That also 0 right there? Okay.
Yeah.
And then we want to also bring it in here and do something to it.
Yeah, so the way that this is going to work is we have SPL0, that's our current sample. We want to assign that to the previous sample. But before we do that, before we overwrite the previous sample, we'll say 2 samples ago equals to previous sample.
Whoopsie daisies, yeah. Oh, it even tells us this stuff. That's awesome. Okay.
Yeah, that wasn't there the last time I was playing around with JSFX. That's new. Cool. That's fun. And you need a semicolon at the end of the line.
And this is not like grammar really matters with computer languages. It just, if you don't put the semicolon, it won't work. So it's not like real life where
yeah.
Cool.
It depends on the language too. Lua is fine without the semicolons. It's in fact, the common style is not to have semicolons. You can have them too in Lua, it doesn't matter. In any case, so think about the order in which the things are happening. You're saying SPL0, our current sample, equals previous sample. So we overwrote the previous sample. And then on the next line, we are saying previous sample equals 2 samples ago. But previous sample has been overwritten. We already lost the previous sample. Do you see the issue?
Yeah, I have to change, let's see, switch the position of these 2 lines, right?
Yeah, go ahead and do that.
Zoop, boop, beep, bop, boop. Okay.
Yeah, so now the first time we run this, can you walk me through what happens not with the average and SPL0 equals XPL1 equals average? We don't care about that. But just go through the sample block and think about the 2 samples ago, previous sample, and SPL0, and walk through that logic to see if it makes sense.
Okay, boop, boop, boop. So this is going at a really fast speed. We are taking 2 samples ago. We are calling it previous sample. Then the next line, previous sample, becomes SPL0. I'm trying to think if I just created like a redundancy. If now 2 samples ago just equals sample 0. Like would those 2 values just always be the same? Well, no, because I'm looking, they're different.
Because yeah, they are different, and you can tell that they are different because when we start running the sample block and we see the line 2 samples ago equals previous sample has not been assigned SPL0 yet. It was assigned SPL0 1 sample ago. So our previous sample variable is from the previous sample. And then we are remembering that value using the 2 samples ago variable. And then we overwrite previous sample. So you have to really stare at this and keep in mind that this is running in a loop and that the variables carry through. The variables that you assign in one run of the loop will keep around with the same values the next time you go around. That's essential. So what we are doing is we have 3 variables, SPL0 previous sample and 2 samples ago. And every time we go around the loop, we are saying, effectively, push everything to, I guess, in my case, to the left, but to your right. But push everything to the left.
Yeah.
You see what I mean? So now we have the 2 samples ago variable. What happens if we replace previous sample on the average calculation with 2 samples ago? And you can remove the multiplication by 1 because that is redundant. But don't save yet. Replace, but don't save yet. And let's think about what we should see. What do we expect to see if we do this replacement? Right now, what we have is a low pass filter. If the samples are changing too fast, our average is saying, whoa, 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 wait right there. You're moving too fast. I will average you out, and the low frequencies, the low rate changes will keep around just fine, but the high rate changes, I will smooth them out. But now I'm looking at 2 samples ago. What happens then?
So I feel like, well, at least in our current formula, then we are basically we're basically comparing like sample number 1000 with sample 998, and we're skipping over 999. Yeah.
And we are doing that with a sliding window. So we are skipping sample 999, but when we get to process sample 1001, then we will look at 999. So we are never dropping any samples on the floor. We are always considering all of them. But now we have this gap. So previously, when we were looking at just a current and a previous sample, we were taking care of very high frequency changes. Now that we are looking at 2 samples ago, we are not looking at very high frequency changes. We are looking at moderately high. We are looking at something more in the middle of the frequency spectrum. And the further we go, the more this will, the more we will notice this, that now we are not smoothing things out. Things that are moving so fast. We are smoothing things out that are moving moderately fast. Does that make sense?
So like high mid, like this area.
Yeah. So save the file and let's see the change.
Wow, beautiful.
So that is what we call a notch filter, right? Yeah, that's a notch filter. So it's just taking some frequencies and making this notch in the frequency spectrum.
That's awesome.
Cool,
so
huh?
Cool. So happy.
And and of course, it would be nice for us to be able to move this notch around. And we'll do that today. But there is still one more thing that I want to play with. And that is, we looked at the previous sample in last week's stream. We looked at the previous sample. So we were smoothing things out. That was a low pass filter. We subtracted, and that was a high pass filter. That's because if you have samples like 0.3 and 0.2, let's say that this is a relatively low frequency change. Let's say that this is not changing very fast. It's not like going from 0.3 to minus 0.7. So this is a low frequency change. So we are going from 0.3 to 0.2. But if we subtract these two, then we get 0.1. So we are making a change that used to be 0.3 to 0.2, and we are making it go from 0.3 to 0.1. So we are making this change go faster. We are increasing the rate of change. In other words, we are prioritizing the high frequencies. So we subtracted and we got a high pass filter or a low cut filter. Now we looked at 2 samples ago and we did a notch filter. What happens if we subtract 2 samples ago? If we say 2 samples ago minus SPL0, what do you expect to happen?
Okay. I mean, my instinct goes the notch filter will then like come around here, like it'll be low mids. But I feel like maybe not. Maybe I'm tricking myself. I don't know. Should we just try it?
Well, so if you want to move the notch around,
Mm-hmm.
what you have to do is look further in the past, or that's one of the ways. There are more intelligent ways, and we are going to talk about this later. But if you want to go further in the past, if you want to go further deep in the low frequencies, you need to go further in the
Mm-hmm.
past. But we're not looking at 3 samples ago. What we're doing is we are taking 2 samples ago and we are subtracting it. So we are now going to emphasize the change from 2 samples ago.
Oh.
If the change was only slight, if 2 samples ago we had 0.3 and now we have 0.2, we are now going to emphasize this change. It was relatively low frequency, going from 0.2 to 0.2, but now we're going to make it 0.1. So we're going to say, because we're subtracting,
Mm-hmm.
0.3 minus 0.2 is 0.1. So we are going to now emphasize this. We're going to emphasize the high frequencies.
Mm-hmm. So we are going to
Isn't
boost.
isn't that mind
It's in
bending?
yeah. It's pretty mind breaking. Um,
Yeah. Yeah, I think that boosting is a nice way to think about it. Let's try it out. Subtract, so change that plus to a minus, and then what we are doing is a 2 sample delay. That's what we did.
mm-hmm.
We did a 2 sample delay. It's as simple as that. So doing a delay and doing an EQ is relatively straightforward. If you know how to do a delay, you know how to do an EQ. And probably the person who was teaching you Max DSP, I don't know how Max DSP works with delay. So probably doing this sort of shenanigans with the samples may not be straightforward, and that's why it would be hard to
Yeah.
do an EQ in Max. Or maybe it's just hard to explain what's going on. I mean, we have been talking for 2 hours to write 5 lines of code, so
Right.
maybe the person didn't want to do that. I don't know.
Yeah, yeah. I think also Max MSP, because Max MSP has these like, and probably EEL2 does. It has these buffer objects, so they're really easy. Like you give it a length, and then it's just putting your audio in a buffer, and then you can recall that buffer for a delay. We later did get into EQ, but it was pretty insane. And again, like there are objects in it, so you're not getting down to this level of doing stuff. You're just calling an object, basically. Um,
But could you do in Max a delay of 1 sample or
yeah,
2
absolutely,
samples?
yeah.
Oh, so you could do an EQ very easily if you
Mm-hmm.
wanted, and it's kind of weird. And you said that probably in JSFX there would be something like that, and there kind of is and there kind of
Mm.
isn't. In JSFX there is one buffer. It is one big buffer of I think about 8 million samples,
Mm-hmm.
and you can write to it, you can read from it, you can take sections of it if you want, but it's one big buffer and you have to manage it yourself.
Mm-hmm. I'm just trying to see length.
Yeah.
That's not bad. That's great.
It is a Yeah, it's like 1 minute or so in a stereo
Oh, okay,
signal.
because times two, yeah.
So you can do something like a looper. In fact, there is a looper that comes with ReaFIR. It's called Super 8, and it is written in
Mm-hmm.
JSFX. So you can do a pedal that is like a looper in JSFX because it has been done. So now save this. Let's see what
Okay,
it looks
drum
like.
roll. Brrrr, tidin. Ooh, okay. So it's not that it
It
boosted it,
emphasized
it
the
like
high
cut
frequency.
things around it.
Yeah, so that is something that we call a band filter, a band pass
Mm-hmm.
filter,
Mm-hmm.
right?
Correct.
And again, we cannot manipulate where our band is. We can only emphasize these frequencies that are emphasized there. And we cannot move it around. We cannot tell how much we want to emphasize this. But yeah, so now we know how to do a low pass. That's the first one we did. A high pass, a notch, And now we learn how to do a bandpass. That is like the basics of how EQ works. I said this before, I'm going to say it again. An EQ, like a proper EQ with many controls and everything, it is just a series of these filters. So if you copy and paste this code and you have a series of these filters and you can manipulate them, you can maybe bring some of them in or turn some of them off, what you have is an EQ at the end. That's what an EQ is, just a series of these filters. And now we know how to do these basic filters.
That's incredible.
Yeah. And thank you both for the kind words on the chat. I'm happy that my JSFX tutorials are helping you out. Okay, so do you want to move on to the real deal? Do you want to do a real EQ in which you can move the filter around?
Yeah, seems like the next logical step.
Yeah, so the principle, we already know. The principle is we want to manipulate previous samples, maybe the previous to previous sample, we want to add the samples together or maybe subtract. In some cases, we want to multiply before we add and subtract. The principle is just that. We are going to do a very short array of 2 samples. And we are going to add and subtract and multiply and divide and very simple mathematics based on these samples. But to have any sort of sane notion of what we're doing with the samples, for instance, if we want to say that I want to boost by 6 dB on a certain frequency, we need to translate this 6 dB into a crazy number that will maybe multiply 2 samples ago by. So we need to translate this minus 6 dB into a crazy number that we can multiply the 2 samples ago variable, and it will have that effect. And the mathematics of how you translate this is absolutely ludicrous, and I don't know any of it. And there are like these thick books, and it's a whole area of research called filter design. I don't know much about this. But what people do is, in essence, they write some crazy mathematics, but also sometimes they just look at how some old EQs used to do things, and they measure things, and they just try to emulate what that old piece of equipment was doing. So you can try to recreate the logic of that old piece of equipment using this digital samples and doing this simple mathematics that we are doing right there. But you have to figure out what are the magical numbers, right?
I have a question actually about that. And this is again kind of, you know, we're having a lot of different kind of disciplines collide, which I really like. So we're talking about maths and we're talking about music. So bringing into that like a kind of sound cognition, like I know that people have done research where they wanted to kind of figure out, what people perceive as being half as loud. So they figured out that if you turn something down 6 dB, most people will say that's half as loud. So my first assumption was that if you want to cut something 6 dB, you just divide by 2. But I guess that's not like, so value of any sample, you divide it by 2. If it's like 0.1, it'll be 0.05. It'll be half as loud, but it's not like that. It's a whole other thing.
Yeah, it is just what you described. If you want to do volume change on all frequencies, you can just multiply the whole thing by half, and you have a minus. You have a difference of 6 dB. And in fact, it's interesting that there is this research. I didn't know about it, because what I do know is that 6 dB translates to half amplitude. So if your number is going from 1 to -1 to 1 to -1, and you multiply by half, you end up with half minus half, half minus half. And that is a 6 dB change. In fact, in the oscilloscope that we have on the screen right now, there is a scale that is in dBs. And if we send a sample that is exactly half, we can do that, right? So just change the last line of the effect from SPL0 equals SPL1 equals average, change the average to say 0.5, which will send half. And we'll see that on the oscilloscope, it will stay at -6.
Yeah.
You see that? So there it is. It is half amplitude.
Very cool.
And I have a video on my channel, by the way, since Bo mentioned my channel, I have a video in my channel in which I explain this relationship between amplitude, 0.5 is an amplitude, and dB, the scale that we use to measure sound pressure. And it is super interesting how this relationship works, and there are some weird, cool mathematics and formulas that use logarithms and everything. And I explain how that works. It's a video about, I forget the name of the video, but it's like the simplest effect explained in detail. So what I do is effectively a volume effect, which is the boilerplate that comes with ReaFIR. But I explain for 1 hour why that works the way that it works. And I explain the weird formulas in that boilerplate. So if you want to understand the boilerplate, go watch that video as well. But that's not what we're here for today. I was saying that if you wanted to boost or attenuate all frequencies, you could multiply by a number like that. But what we want is to attenuate some frequencies. And that is more interesting. You cannot just multiply the 2 samples ago by half. And I guess if you try to do that, what you're going to do is just probably you're going to change the size of the notch. But we can test this and see if that works. But right now what we have is a bandpass. So if you multiply by half, I think that the attenuation on the other frequencies will be less. It's probably not half, but it's less. So we can tell that by multiplying these numbers, we are making this, I guess, the Q of this bandpass go higher and lower. But there is no relationship one-to-one like this. It's not like when we multiplied by half, it went from -12 to -6. It's not like that. It's much more complicated than this. And as I said, I don't know how to come up with the magic numbers, but I do know where to find people who measured old equipment and came up with perfect formulas for the magic numbers, and we can use that.
Cool.
And there is something else I want to explain, which is related to this, because when we dive into these formulas, we're going to see something interesting. What we're going to see is that in the computation of the average, we don't use only the 2 samples ago and previous sample when SPL0. We also use average itself. So when we go to these formulas, they're going to be more sophisticated, and they're going to use the average itself. So as I said, when you go around the loop, the variables retain their values. So when we go around the loop, the first time we go around, average is 0. So that's okay. The next time we go around, average will be the previous average. But then we use the previous average to compute the current average. And we also look at the previous average and the previous to previous average. And we use 6 things in the equations that we are going to look at. We are going to use 6 things. We are going to use the current sample, the previous sample, 2 samples ago, and we are going to use to calculate the average, the previous average, the previous to previous average, and I guess 3 averages ago, something like that. Or maybe just 5 samples, I forget, but 5 numbers, I forget. But the point here is we are going to use the average and the previous averages to compute the current average. Okay? So it's just one thing that we need, because we need to sometimes we need to look at a trend that started way ago to be able to do some sort of high-pass filter and to move the filter around. We'll need to look at things that happened longer ago even than 2 samples. And we don't want to keep 500 samples ago. That would be very expensive for the computer to keep around and to keep averaging these things. And also, it doesn't give us much insight into the filter anyway. We already kind of have a distilled version of that information by having calculated the average 1 sample ago. So we can just use that instead of remembering 500 samples ago. Okay, So there is some fancy terms that I want to throw at you all, because if you start reading about this, you will find people using these terms and they sound really fancy, but they are so simple. And it took me the longest time to figure out what they meant. And when I realized, I was like, oh my God, why are people using these fancy names for these simple concepts? So let me go and put some terms here on the table. The first term is IIR. It is infinite impulse response. What we have right now, or what we are going to develop using these equations, will be one of these guys, an infinite impulse response. Well, and what's this name about? Well, what this name means is when you do an impulse is just a short well, it's a short impulse. I was going to say an impulse is just a short spike. So if you do a sample that is like once followed by a series of zeros forever, that is an impulse. And the filter is going to respond to this sample coming in, right? So if SPL0 is an impulse, it's a 1, the filter is going to respond to that because we are using SPL0 in our calculation. But more importantly, because in the next equations we're going to look at, we are going to use the average to compute the average. This impulse, even if you had just one spike and then an infinite series of zeros, so you do a short spike like a clap, and you never say anything again, it's completely silent forever, the average will always have taken in account that sample from way ago. And of course, the average will be multiplied by a small number, so the effect that the average has will be lower and lower as we progress, so the effect of that clap will be less and less and less and less, but it will be still there forever. It will be super small 1,000 years from now, but it will still be there. So that's what this means. It's a response to this impulse. When you clap, it is going to respond to that clap. That sample that was the clap will be taken in account forever. It's an infinite response to the impulse. But that response will be less and less so over time, I guess. Like after maybe 50 samples, you'll not be able to tell that that impulse was there because the number will be so close to zero that it won't matter. But it will still be there. It will not be zero. It will be 0.00000000001. It will still be there. In fact, because we are using computers, the number eventually will be just thrown out because we are using computers. We don't have infinite memory, so we just round things up. But in theory, the response to the impulse is infinite. So what we're going to do is a very simple infinite impulse response filter. But there is another name that I want to throw because we talked about this last time. I explained how ReaFIR works.
FFT?
And a ReaFIR works using FFTs, and it is a different philosophy to how to do EQs, and it has a different trade-off. It introduces a bit of a delay in the sense that it introduces an offset, and you have to wait a little bit to get a response. And also it uses FFT, so it has that delay because it collects a bunch of samples and then it runs that bunch of samples into this FFT, which is like a black box, a mathematical thing that transforms waveforms and everything. So I was explaining how that philosophy works, and people who are interested can watch our previous stream and explain in detail that philosophy of how to do an EQ. And that's another feasible way of doing an EQ. But if you do it that way, you are doing a block, you take a block of samples, and you pass that block through the magic box of FFTs, which is a mathematical thing. But then you don't use the result of one run to feed on to the next. There is no concept of taking our average and using it to compute the next average. You don't take the result of an FFT to compute the next FFT. You don't do that. So there is another term that people use to to denote this thing, it is a finite impulse response,
Ah, there you
FIR.
go.
And that's why ReaFIR is called ReaFIR, because it's a finite impulse response. Because it's finite in the sense that if you do an impulse, if you clap, the FFT, the way that the ReaFIR plugin works, it will take that clap in account for a block, but the next block, it will have forgotten about the clap. And you will hear these terms. In fact, ReaFIR is called ReaFIR because of this. So you see these terms around, and now you know what they mean.
That's awesome. I know that so many people didn't know, and actually somebody asked on one of the groups once, and nobody who knew responded. So that's cool. By the way, just speaking of, it's somewhat unrelated, but I just find it really cool. Do you know about this software called Spear?
I
Spear
don't think
is
I know
cool
that.
because it
No.
can take audio and it will then isolate it in all the sine waves that make it up. You know, the classic like Fourier analysis. But what's really, 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 really cool is that you can then take that. So speaking of things that kind of end up becoming the same thing, you can export these sine waves as like MIDI, and then make a song that's made, so you can write like a melody that's made up of the, you know, MIDI notes or MIDI, like the frequencies that then we can assign to MIDI notes. So you can make a melody that's made out of the sound profile of a snare. So really cool and free app, which I really like, and it does the Fourier transform basically. So it's taking a window of time and then it's analyzing it, and it's going, okay, it's made up of a few high frequencies there because I see those kind of small changes in time, and low frequencies here because I see those big changes in time. And that, I think, is quite awesome.
Yeah, I didn't know about Spear, but I have seen that fascinating. I mean, you can say something, you can speak a whole sentence, and you can then, I think that the video I watched, it was some video on YouTube, and someone took that MIDI and played it on an actual piano. So the piano was speaking the sentence. And of course, it sounds like crazy. It sounds like you from outer space, but it's still, you can kind of make sense of what the piano is saying.
Yeah, super dope.
Yeah, and in a future episode, I'm sure that we will explore FFTs, and we can talk about the mathematics behind an FFT and try to break apart this black box. It's not that complicated anyway. It's like a formula with 5 variables, or not even that. So it's not that complicated of a concept. I'm treating it as a black box because we only have so much time.
Yeah.
But yeah, so never mind FFTs. We are not doing finite impulse response. What we're doing is infinite impulse response, and all we have to do is find the magical numbers. So I said that we are going to do the state of the art, and I have lied, because the state of the art is this document that if you go to the ReEQ, not the ReaEQ, but the ReEQ, and the person there linked to the paper that has the state of the art in terms of equations for these kinds of filters, and I tried to read that paper and it went way over my head. Okay. So we're going to use something that people used to use and some people still use. They're still good formulas and everything. They're not as sophisticated as these ones, probably, maybe, I don't know. But they're still excellent formulas and they are used all over the place. So the thing that I want you to look for is an EQ cookbook, and we're going to find the same document in 500 places.
Okay. Audio EQ cookbook.
Take anyone. Okay. Yeah, take any of these results. They're all the same document. Okay. They are just styled differently. Okay. Yeah, so this one is kind of interesting because it seems like the web audio API, which is something that you can use in the browser if you're developing applications for the browser. Oh. You can use the web audio API to do synthesis, to do Fourier transforms and everything, and to do EQs. And it seems like maybe they are using this. I don't know, because W3C is the group behind developments in HTML, CSS, JavaScript, and so forth. So I don't know what's going on there. I don't know why they picked up this document, why they formatted it, why they have it in the working group note, but they have it there, and we are going to use it from there. That's fine. You can find this document anywhere. But interestingly enough, many people have a link to the original source, and the original source seems to be offline, but you can find 1,000 copies, and that's okay. So it seems like this person, Robert Briston Johnson, measured an old piece of equipment and figured the formulas that we can use. And in these formulas, there is a place for us to say, what is the frequency? How much do you want to boost or cut? And then we will finally have sliders, as Jancy is asking for on the chat.
Yeah.
So there we go. We have the formula right there. We have one of the formulas right there on the screen. So all we have to do is implement this. Is this difficult to implement? Not really. It's a bunch of multiplication, addition, and division, right? Now all we have to do is make sense of all these parameters, A0, B0. What is all that about? Yeah, so let's first understand the term biquad filter. I'm not sure. I'm not 100% on this, but I think that it means that we are looking at most 2 samples ago. So the filter that we had to begin with, the filter we did last week, was just looking at one sample, and I think that has a different name. I don't remember what the name is. But biquad means that we are looking at most 2 samples ago. And it seems like the technique used to come up with the crazy formulas is this bilinear transform thing. But I don't know how that works. But yeah, scroll down some more, and we're going to find formulas that make more sense. So yeah, okay, we can start to read. Scroll up just a bit. And there are the definitions of some of these weird letters. So when it says capital FS, that's the sampling frequency. In our case, it would be like 48,000 times a second. When we're writing JSFX, we have a magical variable that tells us the sample rate. So how about we read the document? Can you do this? Can you put the document on one half of your screen and then put the JSFX on the other half, and we'll go translating things as we read.
We could get rid of this table of contents here. It's huge. But what else?
Well, just go to any other of those links, and there may not be a table of content on the left.
I will, after the stream, I'll go into like finding the best looking one, I guess, and I'll link that in the description. Let's see. Shipazoo. Let's see what Shipazoo's doing. Okay, this looks, and I like a dark theme text too, so why don't we work with this? Seems like, yeah, same formula here. It's even copy pastable. Yeah. I don't know if that helps us. And here we are.
Oh, it's a little bit above. We were at capital FS.
This main.
Where is it? Oh, okay. It says now given, and then it doesn't have the variable names. It just says sample rate. Oh, okay. So in this document, I think that other version has renamed the variables. We don't care. Now it says sample rate. We don't care. Instead of capital FS, it's saying sample rate, the sampling frequency. It's still the same. It's the sampling frequency. And in our JSFX, we have the system variables on the right pane of the JSFX window. And in there, you can see a lot of information that we don't know about. But if you scroll down, eventually you're going to find something that is the sample frequency, and we will be able to tell that because it will be 48,000.
Oh, okay.
The value associated with it
there you go.
will be 48,000. S rate. So that's a magic variable like SPL0 and SPL1. It's a magic variable, and it is a variable that represents the sample rate. So if you go in your ReaFIR configuration and change the sample rate, that number will change. So how about we, instead of having to translate everything in our heads, how about we say, sample rate was the name that they were using in the doc, right? Yeah, so how about we say sample rate equals S rate? We are just renaming something, but it will make things easier because we'll be able to copy and paste. Yeah, I think that anytime you change the sample rate, it will change the, it will rerun the init block. So I think it's okay for us to do it there.
Straight.
And now the next one is a variable called frequency. The frequency variable is wherever it's happening, man. So that is our slider. So depending on the filter, so this will have equations for low pass filters, high pass filters, notch, band, and some others. And all this, they have some slider. If you are doing a low pass, you have the cutoff frequency. If you're doing a band pass, what is the band that you are letting through? So that is the frequency. That is the frequency that you care about in the specific kind of filter that you're doing. And we'll have a slider for that, I suppose, because GMC is looking for a slider. Let's do a slider for that, shall we? Hey, so you explained in the beginning of the stream how to do a slider, so you can go ahead and just do that.
We'll call this center frequency. Oh, okay.
No, call it frequency. Call it frequencies. Yeah, call it frequency like the, no, lowercase f, like in the document. Okay. That's our variable name.
That. Okay, cool. I'll start it as whatever, 0, and then we want, I guess, 20 to 20,000. And we want to go in increments of, I guess, whatever. I guess we'll talk later if we can do a logarithmic increment or something like that. And then we go, so for the user, I'll put the capital F there. That looks all right. Okay.
Yeah. I don't think you need the equal sign right after the closing bracket. And I have never seen spaces between frequency and the equal sign and the equal sign and 0. I don't know if it works, but it may. You can just save and we will see. But it's not common to see that spaces there.
Okay, seems to work, but
yeah, it works
just to keep
fine.
With the syntax that you see usually in JSFX, I'm going to remove them.
Yep. And next we have a variable called dB gain, which is only used for peaking and shelving filters. So yeah, I guess we'll do low shelves and high shelves as well. And I suppose that's something that we want to give the user control of. So it will be another slider.
Slider 2, we call it dB gain. We'll start it at 0. Maybe we'll do minus 96 to plus 12, something like that, and 1 dB increments. And we'll call this simply gain for the user.
Fair. And it's also not common to have the space after the closing angle bracket, but we saw this last time. It doesn't change the appearance, but it's just uncommon to see that space there. And Bo brings something up. On the line that reads sample rate equals S rate, we forgot the semicolon at the end. So now it's a drinking game. Anytime we forgot semicolon, we drink.
Speaking of drink, I'm going to really quickly grab my grab a little more coffee, and I'll be right back. Okay.
Okay. So everyone who is watching, how are you liking this so far? Do you have questions? Is it making sense to you, or do you feel like, oh my God, what is happening? And does it blow your mind, this relationship between delays and EQs and rhythm and pitch? I find that like, how all these things are one thing. I find that fascinating.
All right. Cool. So we made the dB gain, and
now next we have to say, this is something that people who use EQs are familiar with, like the EQ. So for instance, in a low pass filter, how much of the high frequencies are you cutting? Are you cutting just a little bit, or are you cutting a lot? That is something that we can define in at least 3 different ways. And in fact, you do see in different EQs, you see them using these different ways, right?
Mm-hmm.
Yeah, so in the EQ that comes with ReaFIR, ReaFIR EQ, I think it uses Q, right?
Yeah.
But have you used other EQs in which it uses bandwidth or S, slope?
Yeah, it's funny because visually they look similar, but the values are fully reversed, right? So if you go bandwidth, as you increase it, it gets wider, but Q, as you increase it, it gets more narrow.
Yeah. And we have a choice. Again, this is something that I think we want to present to the user as a slider, because we want the user to tell us how much they want to cut a certain frequency. So we have a choice of how we want to present that. Do we want to present that as bandwidth, or do we want to present it as Q? S is just for shelving filter, so I don't think we want to present S. But we have a choice. Do you want bandwidth or do you want Q?
I like Q.
Okay.
Yeah.
And Q, it says like Q is from the electrical engineering kind of definition.
Right.
And that, I don't know. I don't know what is that definition of Q. I don't know what it stands for. I don't know where it comes from. It is a mystery to me.
I learned it once. I learned it in uni. I'm trying to remember if I remember it. But yeah, I gotta look up my notes. I do keep really good notes from school, so I can find that out and write it in a blog post or something later on.
Cool. But I know that Q, I know the function definition of Q. I know that it will give us a slope. It will tell us how much we want to change. So yeah, go ahead and do a Q variable as well.
And I guess we started at like 0.1. We want it to be from 0.001. We can later adjust these values to like 10 in what increments, I don't know. We'll change this as we go, because these values may be a little weird. Like, how is it starting from this value and then the increment is bigger? I don't know. GenMCE.
Well, the increment is not bigger, it's smaller. The increment is 0.01. So you could say 0.1 or 0.09, 0.11.
GenMC
right?
is asking, will they do anything yet? Well, not yet, because they're not plugged in. So these values are not plugged in. Like, they have a value right now and we can change it, but they are not still doing any processing or changing anything in the way we process stuff, if that answers your question.
Yeah, we'll get there. Give us 15 minutes. So, okay, we are done with the variables that we need to give to the user. Now, the rest of the document continues reading. First, compute a few intermediate variables. Okay, let's compute these intermediate variables. There is a variable called capital A, and we'll compute these intermediate variables. They are only dependent on the sliders. So I guess, for instance, A here is dependent on the B gain, which is a slider. So I guess we should have a slider block to compute this intermediate variables.
Cool. Whoops. Wrong place. Slider block. Okay.
Put the slider block after init. It makes more sense.
Okay, I guess.
Right?
Yeah.
It doesn't matter. It doesn't matter. You can define this in any order, but conceptually, I think it makes more sense because the slider block will run after the init block. I think that ReaFIR gives you that guarantee. It will only run the slider block after the init block.
Makes sense.
And Bo has an answer for us. Q stands for quality and defines the rate of the slope and how well it interacts with another slope.
Cool.
Unfortunately, I don't know what the quality means. I mean, does it mean that if I say the quality is lower, it is a bad EQ? So it's not taking as much out of the frequencies? Does it mean I cheaped out when buying my unit?
I guess what we could have done, because bandwidth is easy, it's just dB divided by octave. So could have been easier, but I don't know, we can stick to Q or we can change that as well.
Oh, you like Q. Let's do
Cool.
Q. And Bo also says, remnant of old analog days when precision in filter slopes were a bit stochastic. Yeah, I'm afraid that I am not at your level. I am not sure I understand what's going on with Q. But okay, let's move on. Let's define the variables. Yeah, let's define these intermediate variables. So we have one called capital A, and we'll use, and it so happens that the syntax used in JSFX is very similar to the syntax used in this document.
Yeah, so good document ship a zoo.
But yeah, so it seems like for peaking and shelving EQ filters, we compute a certain way, but let's not do the peaking and shelving filters right now. Let's focus on low pass, high pass, notch, and band. So we can use sqrt is also the function name. It comes with JSFX, and you can use that. So let's go to the slider block, create a new line, say A equals sqrt.
Oops. Yeah.
And then in parentheses, not in square brackets, but in parentheses. So that bit is a bit different. And then you can say 10 to the power of dB gain, which is one of the sliders, divided by 20.
dB gain. Oh, no, I misspelled it. Chap. dB gain divided by 20, and then close this bracket and close the second bracket.
Yes, and put a semicolon at the end.
Drinking shots.
And by the way, Bo, if you can explain more about this filter slopes and how the precision was bad, was I right? I mean, was it the fact that you cheaped out when buying a unit and then you wouldn't get an EQ that would take out as much of the frequencies? Is that what this is? And then people try to define this quality mathematically? That is kind of crazy. If you want to explain more, I would be happy to hear about it. But let's move on to the next variable. So we have a variable called omega. And by the way, it's kind of blind what we are doing. What are these variables doing? They're going to be used later to multiply and divide the two samples ago variable. Okay, so these A variable, omega, and so on, they will be used later on. But right now we are computing all of these because they will be used. The A will never change. It only depends on dB gain. So as long as the slider is there, A will not change. So we can compute that ahead of time, which makes things faster. So omega equals to 2 multiplied by pi. And the way that we write pi in JSFX is with a $sign and then lowercase pi. It's something that comes with ReaFIR. It's a magic variable, times the frequency, which is one of the sliders, divided by sample rate, which is another one of the sliders.
By sample rate. Beautiful. Oh.
Semicolon. Drink.
There we go.
And then next, we pre-compute the sine and cosine of omega. But we cannot call the sine of omega just sin because we already have a function called sin. So we'll have to call this maybe sin of omega, and we have to remember that later.
Let's go sin omega like this. And cos omega like that. It's good. Seems that a ReaFIR is also suggesting variables that were used earlier, so that's easy. And then I guess sin we just use like this. Cool.
Yes. And right now we are going to do a leap of faith because the sine and cosine functions in JSFX. Okay, two drinks now, one for sine and another for cosine. So they expect the values to be in radians, and I suppose that the formulas here are also given in radians, because people tend not to use degrees for that, but I don't know. We'll see. If it works, it works. If it doesn't work, we have to remember this decision. So next we have alpha, and that is just sin of omega divided by 2 times q, because we define q. If we had used bandwidth, we would need to use the other
I guess
formula.
I guess the question would be, so is there like a EEL equivalent to show console message? Or I guess right now we should see a sin omega and a value somewhere once I save this, eh? So we don't need a show console message.
Yeah, there is no equivalent. There is no equivalent of show console message. The closest thing you will find is something we have not touched. You can do a graphical user interface in JSFX, and it's not just a bunch of sliders. You can have a drawing on the screen. I have videos in my channel in which I go in depth about how to do that. When doing a graphical user interface, you can print strings to the screen, and that's the closest you get to show console message. And it's sometimes useful to have that. But in most cases, just the right pane with all the variables is enough to figure things out.
Cool. Oh.
Semicolon.
When will I learn?
And then next we have a beta, which is the square root of a divided by q. Oh no, that is for shelving EQs only. So I guess we'll use... You know what? Just go ahead and define this beta equals square root of a divided by q, but I think that beta will not be used.
Divided by q.
But we'll see.
Beautiful. I should just do a save.
Yeah.
Yeah, so the sine of omega
yeah,
now...
and semicolon.
Oh.
Semicolon.
The sine of omega now is 0.5, so it's not in radian.
How can you tell? The sine will always be in the same range. The output of sine will always be in the same range. We need to look at omega. Omega is 2.6. So I think it is in radians. I think it's 2.6 turns. But
as soon as I said it, I realized
it could be 2.6 degrees.
I don't have enough information to say
that. We'll see. We'll figure it out. I think it will work. So next, we have a next section that says, then compute the coefficients for the kind of filter that you want. So now we are moving on to computing these coefficients. What are they? They are the numbers we are going to multiply the 2 samples ago, 1 sample ago, and so forth. These are coefficients, and we need to compute them for every sample that comes in, I suppose. Yeah, so how about we start with a low-pass filter, right? It's the first filter we see here, LPF in line, I guess it is 85 or something? 95. No, 105. Yeah, that line. So the first formula we have here is something that we can blissfully ignore. But next, move on to the next lines. So this first line is a transfer function, and it's, I don't know what that is about. But next, there are all this B and A stuff, and these are the coefficients. So I think, if I remember correctly, A0 is the coefficient for the current sample. A1 is the coefficient for 1 sample ago. A2, 2 samples ago. And B0 is the coefficient for what we are calling the average. B1 is the coefficient for what we will call the previous average. And B2, the coefficient for the previous to previous average. Okay, so we are going to compute these coefficients. So go to the sample block, and before any of these lines, so as a new first line, start a new line there, and let's compute B0. It's equals to 1 minus omega cosine, or cos omega divided by 2. So go ahead and do all of these. You may want to copy and paste and rename and put semicolons in place. Do whatever you want.
Forget it every single time too. You got your B1. It is 1 minus.
And while you're doing that, I'll try to make I'll try to make sense of what Bo is saying. I know the Q stuff from speaker design. That's fascinating. Do you work on speaker design, or were you involved in doing that? I would love to hear about it. And the filters had filters. I suppose that the speakers had filters that had to match electrically plus acoustically. Okay. So you were doing a speaker. You were working on the design of a speaker, and you wanted the speaker to have treble control or bass control, like my speakers right here. I can do that. Like maybe to compensate for a problem in my room, I can do a low pass filter, I guess, or a high pass filter. I don't remember. But then when designing the speakers, you wanted to have this built-in EQ, and then if you did it with a low quality filter, it wouldn't do as well, and that went to become the Q parameter. But how is Q measured? What is the unit of Q? How many Qs is a good Q? Okay, so we need to drink 3 times. But it seems like we made it, right?
Yeah, I'm just checking my math one more time. Yeah, 1 plus alpha. I gotta kind of learn to not put redundant spaces. Like with Lua, it makes it better readable for me, but with math, it's like, why are we doing this? Yeah.
Yeah, well, you're going to find all sorts of crazy stuff when it comes to indentation and spacing. Personally, I prefer the spaces like they read in the document with a bit more spacing than you have, but it's fine. And I don't think that B1 is correct.
B1 is minus.
I think you mixed up B1 and B2 there. Oh, and you mixed up the low pass filter with the high pass filter.
Oh, I checked my math wrong. Because I was like, how did I? Okay, and get rid of this boy. Pow. So the rest I think I managed to do. Yep. Yeah, you and Bo should be friends for sure. I think you will have nice chats.
Yeah, Bo did speakers as a hobby. Oh my god, we need to talk. Okay, so now we have all these coefficients. Let's use them, and we'll have a low-pass filter. So I think that the formula we want is above in the document. There will be a formula involving A0, A1, A2, B0, B1, B2, and we need to find that formula.
Doesn't seem to be too much stuff going on. Or oh, okay.
There you go. No, yeah, that one. It's equation 4. So it says yn equals a bunch of things.
So write this in the sample block.
And I think, if I remember, yeah, we're going to write this in the sample block right after this B1 stuff that we have right now, right after this block of variables that we have. We are going to write this, but we need to make sense of this formula. So we are calling our samples SPL0, previous sample, and 2 samples ago. But they are calling the current sample xn, the previous sample xn minus 1, and the previous to previous sample, or 2 samples ago, they're calling it x of n minus 2. It's just a difference in notation. So I suppose that it would be nice if we started calling our variables like that.
Yeah, makes sense.
Too. So how about we say, and we need to do that whole shifting, right? We need to remember the variables as they come in. So I guess one way to do it would be to say, instead of 2 samples ago, let's use x underscore and underscore 2, something like that. Yeah, I was thinking about an n in the middle, so it would kind of read the same as the variable in the formula. X underscore n, the letter n, underscore 2. So it kind of reads like the thing we have in the formula. Unfortunately, we cannot have the square brackets in a variable name in JSFX. So we'll have to make do with that. And then previous sample is x underscore n, x underscore 1.
And I'll just replace that here as well. X_n_1. And this would go, I'll plug it into above. I don't know if we still need to plug it into above, but just in case. And the averages, are those the Y ones below?
No, hang on. We still have a bit more work to do. I think it would be nice to have a variable that reads x_n so that what we end up writing matches very closely to equation number 4. So how about we say that SPL0 equals to the other way around. X_n equals SPL0.
Okay.
So how about we have a line that reads like that? So no, keep the line that you have.
Add another.
Or yeah, you can do it that way as well. You can do it that way as well. Yeah, I know what you're going for. You can go ahead and do that.
Okay, SPL0.
Okay. So let's think about how this is going to run. We will have x n-2 equals x n-1, which is fine. We are doing a shift. And then x n-1 needs to be equal to x n.
Right, so we get 3.
We are shifting everything to the left. There you go, just like that. And put a semicolon at the end of the line, as we all get so drunk. And then, instead of average is no longer a good name for this, right? Because it's not really an average anymore. It's like the output, maybe. So maybe rename this to output or something that makes more sense. Oh, here's a good name. Y of n, because that's naming the formula. So that's our Y of n. So our Y of n will be this big formula, but take a look at the second line there. This formula also involves Y of n-1 and Y of n-2, right? So it's our previous average, our previous yn, and our previous to previous yn. So we'll have to do a similar shifting, the same way we are doing with x, we have to do with y as well.
And so I go y, and whoopsie daisies, 1 minus 2 equals y of n-1, and then y of n-1 equals to y of n, which equals to this formula, which we will now adjust, I'm assuming. Oops, and I gotta check that, and I gotta pow.
And also, now we say SPL0 equals SPL1 equals y of n.
Okay.
And then we have to write the formula for y of n. And it is pretty much the thing you see on the screen. You just copy and paste, or you rewrite it however you want to do it. But that's what you do. You just multiply the values, add the values. You already have all the variables. So just do that and save, and we will have a low-pass EQ,
B0
a low-pass filter.
divided by A0. Or I'll do this quietly so you can talk to Bo or do other things.
Yeah, so Bo said that Bo did speakers as, by the way, Bo, what pronoun should I use for you? He, she, them, because otherwise I have to do some handstanding when I say things like, Bo said that Bo did. So you need filters to divide between the big speaker and the smaller ones, low frequencies and high. Oh, okay, that's interesting because the speakers that I have here, I have this regular studio monitors, and I have a subwoofer and a tweeter, and the subwoofer needs to play the bass frequencies, the tweeter needs to play the high frequencies, and there is kind of an overlap, and that overlap needs to be very carefully done so that the frequency response is good. It's relatively flat in the case of studio monitors where you want that flat response curve. So yeah, you need to apply some EQ to the the subwoofer to take out some of the high frequencies and vice versa for the tweeter, and you want that to be very precise. So I guess the higher quality you have, the better you will divide between subwoofer and tweeter. Is that what this is about? Did I get it right? Okay, so Bo, hi, he, can you, uh, is that what you were doing? The filters to do a subwoofer and a
While
tweeter?
Bo
And meanwhile,
responds,
it seems like you
no,
finished, right,
I'm
Ari?
not finished. I was gonna ask you. So, okay, this formula is too big. So if I want to just spread it in two lines, if I don't put the semicolon and just go to a new line, will that work? Or okay,
Yeah,
so
that's fine.
I'll do
Yeah.
this, and yeah, I still have one half of the equation to go.
And meanwhile, I'm gonna check. You can also, in JSFX, the space in almost every place is not significant. So you can align things the same way that they are aligned in the document, and you can put the minus right
Oh,
below the
okay.
plus, which looks super
Neat,
neat.
neat, neat. A1, A0.
And I'm double checking that you are
Thank you.
spelling everything correctly, and you are.
So far, so okay. Two.
And Bo, I don't think you did all this filtering stuff digitally, I suppose. I mean, I don't think speakers do that digitally. I think they do that with physics and electronics and circuits. So do the circuits resemble in any way the logic of what we are doing? Do the circuits do a one sample delay, or, well, it's not samples really, but do they do a short delay and mix in the signals in some way? And of course, you can also do attenuation by putting a resistor, I think. So you put a resistor to attenuate, and that resistor will do the multiplication by a certain number the way that we are doing. Is that how this works? That would be awesome. If you could do with real world components the same logic you do digitally, or actually the other way around. We are trying to emulate a digital, an analog EQ here with our equation,
Cool.
which seems to be correct. So I think you did all the translation to JSFX from mathematics correctly. So save and let's try this out.
I saw some volume dippage, so that's a good sign. Let me just. I wish I had two screens and I could broadcast two screens, but hey, we can't do all the things. Yep, we got ourselves a curvy low pass. A very kind of ramped.
So now move a slider and let's see that curve move.
Interesting. This is, I'm looking at the wrong thing. We need the Command Shift F3. And let's move the Q. Yep. Okay, and yeah, you see, because we gotta dial in these values because there's a sudden jump because my increments, like a lowest value we set at 1/1000th. If we do something like this, there won't be that big jump. Oh no, there still is. So I guess we gotta figure this out. And frequency, the big. There we go. Very nice. Again, there's like a big jump suddenly. So I gotta.
Yeah, so that's something you need to know about these sliders that come with JSFX. If you have too many values, the slider becomes jumpy. And by too many values, I mean either your range is too big or your resolution is too small. So the slider needs to occupy too many spaces and there are only so many pixels on your screen. So we have a range that is very large. We are going from 20 to 20,000. And we are going in increments of 10. So one thing you can do is just stretch the window so you have more pixels to play with, and that helps. But ideally, we would come up with something else for this. Some maybe decrease the resolution or do some other logarithm thing
Can
like
the increments be
suggested.
logarithmic?
No, but you can instead of using frequencies, you can use octaves.
Oh, beautiful.
I don't feel like that's natural though. But I don't think that's natural though. We usually don't think in terms of octaves when working with EQs, I
Rarely,
don't
yeah.
think, right? Yeah. So I don't know. We would have to figure something out. But it seems like when you change the frequency does change, the cutoff
Yeah.
filter does change, and the gain, if you change the gain,
Well, so I guess,
does it change something, or was
yeah,
it
because
just
I
for
guess
the
gain means
shelf?
nothing in a pass filter, right? It's just frequency and Q. So yeah, the gain is not
Yeah.
doing something right now. The Q is doing stuff.
We didn't use we did not use the A variable anywhere, and we did not use
Right.
beta
We did
anywhere,
use, yeah, yeah, you're right. We
right?
didn't use beta anywhere. We used alpha, but not beta.
We only used omega. Omega is based on the frequency, and we use the sine and cosine of omega to compute all our A's and B's. So A, capital A, and beta are not used. And also alpha is not used. But it will be used for the A's and B's of some other filter. So it's okay that we have these lines there. So yeah, there you go. Now we have an actual slider that does an actual thing, and it kind of works. You look at the EQ, you look at the spectral analyzer, and
Mm-hmm.
it does change. It is
One thing
working,
I want to look
right?
up, maybe in this document, is like the range of Q, like if there's a recommended range of Q, because I feel like some of these values work, and like when we get down here, like this is not the normal Q behavior. Um, it seems to cause like a
Mm.
really, so I feel like, yeah, like 0.17 is good. As soon as we start dipping below, it's starting to do something kind of nuts, bringing down the volume of everything. So
Well, but isn't that just a very large filter that is filtering everything in the
yeah,
spectrum?
like yeah, not to get too greedy, I guess. Like my favorite EQ that I use on almost everything is this one. So this one, I guess, does a little bit of extra math magic, which is very cool. So as you adjust the Q, what it makes sure of is that the loudness boost that it's causing stays consistent, which is very cool. So if your Q is really sharp, it's causing like X dB of gain um, increase. As you bring the Q down, it makes sure to spread it in a way that it would still cause the same amount of increase, which is incredible and very complex, but really nice from like the user point of view. Because as you adjust the Q, you're not artificially creating a lot of boost, and that kind of tricks your ear into thinking something sounds bad or good. Um, yeah, but anyway,
Hmm.
that seems.
But let's go to a simple. How about you said that maybe the range of Q wasn't satisfactory. So how about you just pull in the RIA EQ and we
Oh,
copy the
beautiful.
range from
Ria,
there?
not Re.
Yeah, RIA, the standard thing
I
that comes
didn't
with
know we
ReaFIR.
can change. Oh, I guess we can look under the hood, but we can still look at. Oh, and its bandwidth.
No, just take. Oh, it uses bandwidth. Okay. I thought it
It
used
goes
Q.
from 0.01
Do you
to
have?
4. Do I have something with a Q?
Yeah, and there is in that document. There is in that document that we were using, there is a formula that translates from bandwidth to EQ and vice versa. I don't know if it has both ways, but I know that it has at least one direction. Um, yeah, you can try to look it up and then you.
I don't see anything here. What if I just like Google something like EQQ range? Maybe we get lucky. No, it's all. Waves, I got a bone to pick with these people because they make looking stuff up very hard by how much they advertise. Um, or I guess, yeah, let's maybe grab an EQ that has a Q value. Well, actually, my Aosis has a Q value. So this Q value goes from
Copy
7.
the. Yeah.
Yeah, 7 to 0.1. Okay, that makes sense because actually I think once we go below 0.1 is when it starts to get weird. So let's make that 0.1 to 7, and let's go in increments of 0.1 for now, and let's save it. And okay, it already looks way better to me. Cool, cool.
Great.
Very nice.
And Bo is saying that he used to do speaker design analog using capacitors and everything, but active monitors use digital filters. I didn't know that. I thought they would be analog. And you can scale the slider values with a formula in the slider section. Yeah, so we can present to the user a slider with another unit, which is not frequency or not Q or not gain. And we can translate that using some formula. And that's more or less what we are doing. In fact, we are translating from, for instance, from dB gain to A, which is the thing that we would use in another filter. And it's something that I guess, as Bo says, you can do that with a dB to amplitude. And I guess that's what's happening. The A is related to the amplitude. I don't know what A stands for, but it may stand for amplitude. And yeah, it's something that we can do, but we have to think about it in terms of the user interface and the ergonomics of this. Probably what people care about is either the frequency or the octave, but that is just a preamble, right? Everything we did right now is just to understand EQ because our intent is to do a game with this. So I guess we will not present the frequency. We will come up with a random frequency and then have the person guess the frequency.
Exactly.
So that's a whole story for another episode because we were exploring the mathematics and the physics of how EQ works.
Mm-hmm.
Right?
Yeah, absolutely.
And I think we pretty much reached the finish line for the low pass filter, but there is homework. We have a high pass filter, a band pass. Oh, and there you go. There is the formula that you wanted.
Oh, cool.
It has a constant peak gain or a
Beautiful.
constant curve gain. I don't know which one you want, but it seems like you can do that magic by using one of these formulas.
Mm-hmm.
And we have a notch filter and an all-pass filter, which is nonsensical. Why would you want to pass all frequencies? Because you want to fix something in the phase shift that may happen in an EQ. But that's a whole nother story. And
Maybe
there is
what
a
I
peaking
can do
EQ,
is
shelves.
like plug all of this stuff into the EQ without like having any of them be active. Just kind of write them in, or even write them in a Word document, so that when it's time, I'll just copy and paste from there. For
Yeah. So here's what. Do you want to have homework?
Sure, I love homework.
Okay. So here's a homework. There is a special kind of slider that is not presented as a slider. It's kind of a hack. It is presented as a drop-down menu, and you have different options there. So your homework is to go to the JSFX documentation and learn how to write that down.
Okay.
It's not too hard. You just have to specify the slider in a certain way. It is in the ReaFIR website for how to do that. And then you have a drop-down with all these kinds of filters: low pass, high pass, band pass, different kinds of band pass, whatever. So you have that.
Cool. Sounds good.
And then you can select the kind of filter you want. And when computing, the only difference between all these filters, the only difference will be in this block that computes A's and B's, right in the beginning of the sample block. These 6 lines, they are the lines that are going to change. The rest of the code, you must not change. The formula that computes yn, you don't change. You don't change any of that. You just change these 6 lines. But what you have to do is to check, am I doing a low pass filter? So I'll use these 6 lines. Am I doing a high pass filter? I'm going to use these other 6 lines. So effectively, you are going to do if then else.
Oh, cool. Okay.
But the syntax to write if then else in JSFX is completely nonsensical. So you can look it up on the docs, but I'm also going to give you one example here in the chat. I'm going to paste an example of how to do that because it doesn't make any sense on how you write that. So the way you write that is, I'm going to say it out loud as I type. So you'll have a condition that will be your slider. So maybe it will be like the filter type. And then what you do is you put a question mark, and in parentheses, you put a block of code. And then you put a column, and in parentheses, you put another block of code. And it will come up in the chat in a moment. Sure. And you can put semicolons, you can put new lines to make this look better. It really is up to you how you want to format this.
Fun stuff.
Like this. Okay, so the line is right there on the chat. And does that make sense? Filter type, it will be your variable. So maybe you will have something like filter type equals. So that's another thing about the weird sliders that are drop downs. They are like filter type equals 0 or filter type equals 1. You will not have names for this. You have numbers for this. But maybe your filter type equals 0 and then question mark and then a bunch of computation like this. Like what I just typed.
So it's like if filter type is A, then B0 is this, B1 is that. Okay, cool. And then if it's 2,
yeah. Cool. Yeah, and of course you will want to chain this because you don't have only 2 types of filter. You have more of them. So what you're going to do is just chain this, so you'll have something more like. Okay, it gets very strange when I'm still typing.
I should have. Oh, we have a trick actually for you to commandeer the screen as well if you want to do that.
Oh, okay, but that's not necessary. I typed on the chat the thing you'll probably need. So filter type equals 0, that's maybe your low pass, and then you put all the 6 equations for low pass. And then you chain, you put column, and then you chain. You say, okay, now I will do another one of these if then else's. So you're saying if then else if else if else if else if else if, and that is going to be a chain of these guys. And maybe at the end you'll have something else because it will be the default filter type or whatever. Cool. So yeah, that's your homework, to come up with a slider for the filter type, do this conditional that I copy and pasted, but you have to elaborate on this, and then do all the equations for all of them and see if they work.
All right, I'll give it a go, and hopefully I won't break anything, but hopefully I'll be able to do it, and if I couldn't, that's part of learning. Cool. Well, yep. Awesome. Should we call it?
Yeah, so maybe next time, do you want to keep doing this? Sure, do you want to meet next Tuesday? Yeah, so maybe what we're going to do next time is more of the game part of this, because we already have the filters. And then we will come up with a random filter type and a random frequency, a random queue. And we will try to make the user come up with answers and do more of the, and then we will do more of the JSFX programming really, because we'll have to look at how to do, come up with random values and how to get input from the user using their sliders. And I guess we'll need some kind of output to the user to say you guessed it right or wrong. And then there will be more JSFX programming. So far, all we've done is a lot of mathematics, some copying and pasting, but we didn't write a lot of code. I mean, the whole effect is like 20 lines of code, and it's doing everything. It's doing a professional low-pass filter. Yeah.
Awesome. Thanks so much.
And that's expected. As I said in the previous stream, all the filters and effects that you use, like the one you showed, and the stuff from FabFilter and whatnot, I don't think that they're using these formulas anymore. So I think that they're using a slightly more sophisticated version, but the principle is the same. It's still just collecting a bunch of samples and doing simple arithmetic with the samples. what you're really paying for is the user interface, the ergonomics,
Mm-hmm.
things like matching a filter to a kind of input, all the shenanigans that come around an EQ.
Mm-hmm.
But the principle behind it, the equations and the mathematics of a filter of an EQ, it is what is on the screen. It's not crazy stuff. I mean, it's not trivial, but it's not rocket science.
Right. It's not some like code that they invented that nobody else has. Because I know there's always like debate. Oh, what's the best EQ? It's like it's kind of they're all kind of the same. One has 24 bands, one has 8, one has this type of Q, one has that type of Q. Ultimately, they're doing
Yeah, the
similar
bands.
things.
That's so interesting. There are some EQs that only come with 4 bands,
Mm-hmm.
which is crazy, right? I mean, all you have to do is put more of these guys that we developed in a row. That's what 4 bands are. 4 of these in a row, or 10 of these in a row, however many of these in a row you want. So to limit the amount of bands, it is definitely something that is, in terms of ergonomics, it makes sense, but the mathematics of it is just trivial. You could have however many bands you want.
Yeah, exactly. And it's nice actually, like, I guess part of the appeal of like analog emulation EQs and stuff for me, it's like the API 550, it limits your choices, but it seems like those choices were made by like audio engineers to be somewhat musical. So like the frequency amounts you can choose, they're not any number between 20 and 20,000, but the numbers kind of make sense together, which I really like. And also just no user interface kind of makes you like try to hear them rather than try to see what's going on. Yeah, so all of that stuff is fascinating. And this is the perfect case of like, oh, the more you know, the more you realize you don't know. So as soon as we start talking about this stuff, it's like, oh wow, then what? How do they do this in electronics? How do speakers work? Uh, Analog, digital. The more you learn, you're like, wow, there's so much more going on.
Yeah, and I suppose that these formulas we are using were generated by analyzing one piece of hardware, and maybe other EQs are based on different pieces of hardware, or maybe completely digital and mathematical things that are not trying to emulate anything. So we cannot really say that all EQs are the same,
Mm-hmm.
but the principle behind their work is
Mm-hmm.
all pretty much always similar, and it's just coming up with different formulas with different crazy ideas and cosines and sines and numbers like that. But the principle behind an EQ is just a very short delay, and a delay that feeds on itself. So this thing that we are doing where we are using the average, what we are now calling yn1 and yn2. So we are using the average to compute the next average, the infinite response stuff. I can think of that as a feedback on the delay.
Mm-hmm.
So it's still just a very short delay of 2 samples. That's what this is, a very short delay of 2 samples, and you are weighting the, so you can say the wet and dry signal of the delay, and you are
Right.
doing a very careful wet and dry balancing so that you get the sonic effect of boosting or taming some frequencies.
That's cool. That's very cool.
Yeah, and finally, Bo is suggesting that you can check other JSFX to copy and paste stuff from there to know how they are doing the conditional slider. That is a fair thing to do. What I learned, the way that I learned the most, not only about JSFX, but about audio processing in general. And that's what I love about JSFX. I can always edit, so I can always look at the source and see how they work. And that's how I learned most of the things that I know in terms of audio processing. And it's also a fair way to learn the syntax.
Mm-hmm. Yeah, that's what I'm planning
Uh,
to do, and I'll read the manual, but I always feel like the manual was written in haste, and I just like looking at things and kind of trying them out, and I always try to learn.
Yeah, the manual I think is written from a perspective of someone who knows digital signal processing. They're just trying to get something out. Um, and I had a hard time figuring everything else because I didn't know about audio processing. I learned from reading that. And then they would say things like, this is just a function that does FFT. And I was like, what's going on there? oh, this is just a function that does a permutation of FFT outputs. And I was like, what is that? What is a convolution? What is that? So I was like figuring things out. But I started with the JSFX documentation and reading some other effects. And Bo says, that's why I'm rooting for other forms of averaging. Yeah, we are using these formulas that are made for EQs, but we could use things for like economics and see how they fare and see what they do with this sound.
The Wall Street EQ, I like it.
Yeah, and also image processing, Bo brings that up. There are things that you do with video and photo that relate to things that you do in audio because of the thing we mentioned before. Audio is just a certain wave length, and light is just a higher frequency wavelength, but it's also electromagnetical, but it is a wave. And some of the things you can do translate. So you can do a high pass filter or a low pass filter in images or video, and you can do even things like delays. If you do a delay on a video, what you're doing is you're showing a frame again on the next frame. So it starts to blur in time. That's a blur in time effect.
Yeah.
Yeah, so you can do all these things in video as well. And you can do FFTs in images. You can do a two-dimensional FFT because in video or in images you have two dimensions. It's not just time.
Right.
It's also time and space. So you can do it's not only that, you have two dimensions on the image. So you can do FFTs and do things like Fourier transforms, and you can do the principle behind ReaFIR. You can do that in images as well.
Sick.
Yeah.
Very cool.
It's like all kinds of things that we can learn. And we can try to translate maybe some of the ideas used in image processing to audio and vice versa and see how they fare.
For sure. I'm very excited.
But I would like to finish the game, so I think we should just do the formulas that we have and try to come up with a game.
Yeah. I'll do that, and yeah, so we'll have the formulas ready, and then I'll figure out the drop down, and then we'll try to work the logic from there.
Yeah, let's wrap it up.
Awesome. Thanks as always. Fun is part of my week, and I'm happy that now we're doing this 2 days. So tomorrow, same time, we'll be on Leandro's channel. The link of that in the description. So, give that sub, come check it out. And yeah, we're not doing coding, we're doing something else. So we'll see tomorrow. I'm coming into it with very little stuff prepared, and we'll see how we get on.
Yeah. All right. Cool. Thank you all. Thank you, Aria. And thank you everyone who was in chat and watching us later in the video on demand. It's always nice to be here. I'm glad you are all here. And I see you on the next one.
See you all. Adios. And yeah, peace out. Peace in the Middle East.
Yeah. Now let's do the awkward part where we go to YouTube and stop streaming.
Cool.